We are going to look at the next lesson in this Forces 2 topic, which is forces and extension. Materials like springs, rubber bands and elastic will extend, get longer, when a stretching force is applied to them. The greater the stretching force, then the greater the extension. The extension is equal to the new length minus the original length. Okay, we need to be clear what we mean by extension. Extension means to get longer. But in physics, there is a very short equation that you need to know. The extension is equal to the new length minus the original length. So let's use this equation in the table below to work out the missing values. So we start with the new length, and we have to subtract from the new length the original length, and from that we can work out the extension over here. Okay, so it's going to be 1 minus 2, okay, to get 3 over here. Right, so let's delete those marks and let's see if we can work out what the missing values are. So in this one here we've got the new length is 2, and that's subtract 1, so the extension must be 1. The same thing underneath. The new length is 5, and we're going to subtract 2.5 from that. So 5 minus 2.5 is 2.5. Now, a bit more complicated underneath because we need to work out what the new length is. So to do this, we're going to add the extension to the original length, and we should get 4.5. Same pattern underneath. We're going to add the extension to the original length. We're going to get 3. Okay, so how do we get the original length? Well, this is the new length, 4, and we can subtract from that the extension. So the original length must be 2. Apply the same pattern underneath. The new length minus the extension is equal to 5. Okay, in materials science, there are two basic types of material. We get elastic materials and we get plastic materials. Now, today's lesson is really about elastic materials, but you should know what we mean by a plastic material as well. So let's fill out these missing words. Some materials are called elastic because after they have been stretched or compressed, they return back to their original size and shape. Other materials are called plastic because they are permanently deformed and do not return to their original size and shape. Now, there is a required practical for this particular lesson, which is all about stretching springs. And there is a video which I do want you to watch. It's been produced by Malmesbury School, which is down south, and they've produced a fantastic video all about how to do this required practical. You can find a link to that on It's Learning, and I want you to watch that video. It's about 15 minutes. Now, the data from that experiment on the video I've recorded in this table below, and what you can see here is let's just talk about this apparatus. So we had a spring here. Here's the spring. There is a clamp here and another clamp here. Now, the first clamp, number 1, holds the spring, and on the end of the spring we have a hanging mass. There is a pointer from the bottom of the spring here, and it goes towards the ruler. We call this a fiducial marker or a fiducial pointer. It points at the ruler so that we can get accurate measurements of how far the spring has stretched. So it helps to make this a more accurate and precise experiment. This clamp here, number 2, the second clamp, holds a ruler in place. Now this ruler needs to be vertical, so how would you check that the ruler is indeed vertical? Well, we can use a set square. So a set square, you've got one of those hopefully in your geometry set, and you would set it on its side like this, and you would make sure that the ruler is vertical. And this is a good point to remember in the exam if they ask you a question about this. They might say, how would you make this experiment more accurate? You could say, make sure the ruler is vertical using a set square. You could also use a pointer from the spring to the ruler to make it more accurate. Okay, let's look at the results. We have added weights, started with no weights, and then we've got 1, 2, 3, 4, 5 weights. And they will be added on here. So we're going to start with 0, then 1, then 2, 3, 4, 5 weights. And as we add the weights, the spring gets longer. Now the original length of the spring, which is from the top to the bottom like that, is 2 centimeters. Every time we add a weight, the spring gets longer. So you can see that when we add 1 weight here, we can see that the new length was 5.5. Now to work out the extension of the spring, we have to go 5.5 minus 2. And it's that way. 5.5 minus 2 to get 3.5 centimeters. So the actual extension was 3.5 centimeters. Now we have to convert that to meters. So we divide by 100 and we get 0.035 meters. So a very, very straightforward experiment where we are adding weights to the hanging mass here. We record the new length, subtract the original length to find the extension, and then we need to convert that extension into meters. The next stage of this practical is to plot these results on a graph. The next stage of the required practical is to plot a graph. We normally plot the force, or the weight, on the y-axis, which is vertical, against the extension in meters on the x-axis. Now we need to plot the points, so I'm going to do that, and the scale is already here. So here is the data, okay, force plotted against extension. You can see that the points appear to be following a straight line. Indeed, we can draw a line of best fit which goes very close to all of those points, and it also goes to the origin of the graph. So where is the origin? The origin is here, 0, 0. And it's very important that the line goes through the origin and through as many of those points as possible. Okay, we've got 2 questions. Question 1, calculate the spring constant from the gradient. I will explain more about the spring constant on the next slides. The second question is, what kind of relationship is there between the force and the extension? Okay, let's tackle first of all the calculation of spring constant. Now, the spring constant is the gradient of this graph. The spring constant is how stiff the spring is. It's equal to the gradient. We calculate the gradient by the change in y divided by the change in x, and we need to have a triangle drawn on the graph like this. So you don't need to shade it in yellow if you did this, but you need to draw a triangle so that we can work out the gradient, and it should be a large triangle. Okay, we need to know the change in y, which is this one here. This is what we call the change in y, delta y. Remember, delta is that triangle symbol, and it means change in. And we can see that the force changed. Okay, we also need to work out down here the change in x, okay, which is the horizontal change from here to here, and the vertical change delta y from here to here. So you would draw these marks on the graph and actually record these values. Okay, let's have a look at what they are. We can see that delta y is 5.8. This is 5.8 here, and it goes down to 1 here. So the change in y is 4.8. Okay, 4.8 newtons. The change in x, well, it goes from 0.25 down to 0.04 here. So the change in x is 0.21. To get the gradient, we need to divide those two things. So we're going to have delta y divided by delta x, which is here, which is 4.8 divided by 0.21, and the answer we get is 22.86 newtons per meter, and that is equal to the spring constant. Now the second question. What kind of relationship is there between force and extension? Well, the thing to notice from the graph is that the line of best fit is a straight line through the origin. Therefore, it is a linear relationship. Linear means straight line. But we can go one better than that. We can say because the line of best fit is a straight line and because it goes through the origin, remember the origin is here, we can say that extension is proportional to force, and that is a key word to use, proportional. What does it mean? It means that if I double the force on the spring, if I double the weights, the extension also doubles. If I treble the force, if I put 3 weights instead of 1, the extension trebles. You need to be able to interpret a graph like this, and they could ask you about this sort of thing in the exam. So here is the conclusion to the required practical, and you should learn this. The line of best fit is straight and passes through the origin, 0, 0. This means the extension of the spring is proportional to the weight or the force. Proportional means that when the weight is doubled, the extension is also doubled. The gradient of the force extension graph is equal to the spring constant K. The spring constant tells us how stiff the spring is. Robert Hooke was a very well-known scientist about 300 years ago, and he came up with a law to describe this relationship between force and extension, and it's known as Hooke's law. You need to learn the law and you need to memorize the equation that goes with it. It's very straightforward. Hooke's law says that the extension of an elastic material is proportional to the force applied to it. This means that when the force is doubled, the extension is also doubled. It can be expressed mathematically by the following equation. F equals K times E. You can see the triangle at the bottom right. F is the force in newtons, K is the spring constant, newtons per meter, E is the extension in meters. It's very important that we have the extension in meters. You need to learn Hooke's law, you need to learn the equation, and you need to do simple mathematical calculations using this equation. Now, Hooke's law does not apply to every material. I want us to look at these materials here and think about which one does Hooke's law apply to. So we are looking first of all at this here. This is copper. Copper is typical of a metal. It has a straight section, so this first bit is straight, and then it seems to bend and stretch a lot before breaking. Now, there is a straight section here, so the straight bit, which is from 0 to P, does obey Hooke's law, but after that it does not obey Hooke's law. So this region here is what we would say is obeys Hooke's law. I can't write very well with the mouse pad, but this obeys Hooke's law. Okay, just call it HL, Hooke's law. And this section up here doesn't. Let's look at the next one, which is glass over here. Now this is much more straightforward. We can see it's a straight line and it goes through the origin here. So glass does obey Hooke's law. Okay, it gets to the end here, then it fractures. But whilst it stretches, glass does actually stretch a little bit, and it does obey Hooke's law because it's a straight line graph. Okay, let's look at the final one here, rubber. Now rubber, I think you can see, does not obey Hooke's law because there are no straight sections on that graph whatsoever. It's a curve, it curves all the way, and therefore it does not obey Hooke's law. Now let us have a look at the graph underneath. There's a few things that we need to point out. So we have here a straight line section, which is called the elastic region. This obeys Hooke's law. And then we get to a point here where it's no longer straight. This is called the limit of proportionality. Beyond this region, the graph or the material stretches out. The extension gets a lot bigger. And this is called the plastic region. And once it stretches beyond this point, the material will not return to its original shape and size. Eventually, however, the material fractures and breaks, and it won't stretch anymore beyond that point. Okay, when we stretch an elastic material, we have to work hard. It takes effort to stretch springs. It takes effort to stretch elastic materials. Now we've got here a bull worker at the top, and we've got a bow and arrow at the bottom, both of which take considerable strength to stretch. We say that you have to do work in order to stretch them, and when you stretch them, we are storing energy in the material. So looking at this example here, we're using chemical energy which is stored in the person, and then when we pull the bow, we're doing some work. We have to work to do that. We have to work hard, and work done means that energy is being transferred from chemical energy through to elastic energy, which is being stored in the bow or in the elastic material. And when we let go of the bow, that elastic energy is used to propel the arrow forwards. Okay, this is slightly more mathematical, but not too much, so please keep listening. Now we've already looked at the graph of force against extension, and we've said already that it's a straight line graph because force is proportional to extension. The work done in stretching it is the force times the extension, and that represents the area under here. So this area, which is shaded in blue, represents the energy which is stored in the spring. Now we can show that area is equal to this equation here. We can work out the area under the curve by using this equation. Now you don't need to know how we derive the equation, but you do need to know how to use this equation. You are not expected to remember this. It will be given to you on a formula sheet in the exam, but you will be expected to use this equation, and it tells us how much energy is stored in a stretched elastic material. So EE is the elastic energy, and it's equal to half times K times E squared. K is the spring constant, E is the extension, and in this example we are squaring it. Okay, thank you for listening to this video. I hope that you've understood what I've said. If you need to play it more than once, then please do, because there are some important points in this video and things which may come up in the exam, so it's worth looking at this twice. I would like you, after watching this, to do the mini quiz on its learning, and we will practice using some of the equations. There won't be anything too hard in there, but you will be expected to use the 3 equations that we've come across today, which are highlighted in the video. Good luck.